Hello and welcome to today's panel presentation titled SPEAR, a homogeneous immunoassay merging protein quantification with the sensitivity, simplicity, and scalability of nucleic acid testing paradigms. This webinar is part of the 13th annual event in the Neuroscience Virtual Event Series. I'm Oliver Tassinari, Head of Business Development at SPEAR Bio, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and sponsored by SPEAR Bio. For more information about SPEAR Bio, please go to www.spear.bio. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to first participate by communicating with other attendees using our live chat feature during the presentation. You can find the live chat located at the left of your screen. If you have trouble seeing or hearing the presentation, click on the Help Desk button located at the top of your screen within the navigation bar or from the lobby within the event. Now let's get started. I'm very excited to introduce today's speaker, Feng Xuan, co-founder and CEO of SPEAR Bio. For a complete biography on our speakers, please visit the Presenter tab from the menu on the left of your screen. I'm now going to hand it off to Feng.
Thank you, Oliver, and thanks to everyone in the audience for joining me today. I'm excited to introduce you our SPEAR technology. In this section, I will share the inspiration behind the SPEAR, its development, and how it fundamentally differs from conventional ultrasensitive immunoassay technologies. I will also present key performance data on several low-abundant neurobiomarker assays developed based on SPEAR, and discuss both current application and future possibilities. Nucleic acid biomarkers have long benefited from exceptional analytical sensitivity. With polymerase chain reaction, even a single copy of a nucleic acid can be exponentially amplified, generating billions of identical sequences for detection, even with a portable equipment nowadays. In contrast, protein and peptide lack a natural amplification mechanism as a nucleic acid. This fundamental limitation makes it extremely challenging to detect a single protein peptide molecule in a sample, even with the most advanced methods and instrumentation available today. The majority of immunoassay methods for protein biomarker measurement rely on wash steps to separate the target-specific binding from non-specific binding, generating a detectable signal. Among the most effective and sensitive technologies for protein biomarker measurement, they are immunoassay PCR, electrochemiluminescence immunoassay, eClear, digital ELISA, and the nucleic acid-linked immunoassay sandwich assay, also called the NULISA. Immuno-PCR achieves a higher sensitivity by using PCR to exponentially amplify both the signal and the background. The other three methods primarily focus on reducing background to achieve higher sensitivity. eClear uses electrically controlled signal generation, which minimizes bulk background. Digital ELISA employs a single molecule approach to isolate the true signal from the background interferences. NULISA utilizes a dual capture and release mechanism to more effectively remove non-specific binding. This advanced method significantly improve the analytical sensitivity for protein biomarker measurements. However, this increase in sensitivity comes with trade-offs. First, compared to conventional ELISA and chemiluminescence immunoassay, these advanced methods involve more intricate workflow and specialized instrumentation. Second, the sensitivity performance of these methods heavily depend on the availability of high-affinity antibodies. Third, to achieve optimal performance, these methods typically require precise control over surface chemistry to minimize non-specific interaction between the solid surface, the antibodies, and the targets, which oftentimes can be very challenging. With this technology push the limits of a protein biomarker detection, they also introduce new challenges in assay development and implementations. Some immunoassay technologies eliminate the need for wash steps and the surface immobilization of antibody, such as proximity ligation assay (PLA) and a proximity extension assay PEA. This approach uses two antibodies, each carrying half of a signal-generating moiety, which comes into proximity when binding to the same target protein. This proximity enables a reaction that generates an amplifiable signal. The key advantage of this method is that unbound antibodies do not need to be removed for signal detection, allowing direct measurement of protein analytes in a homogeneous solution rather than on a functionalized solid surface. It helps overcome the limitation of heterogeneous methods. However, the signal-generating moiety on unbound antibodies can also react through random collision and diffusion in solution, leading to target-independent background. While reducing antibody concentration can lower the backbone levels, it cannot be decreased beyond the threshold required for effective binding, which places practical limits on achievable sensitivity. The technology we're introducing addresses the sensitivity limitation of conventional proxy-based methods, while fully realizing the advantages of a wash-free homogeneous immunoassay format in specificity, simplicity, and consistency. We call this technology SPEAR, which stands for Successive Proximity Extension Amplification Reaction. Its mechanism is illustrated in this animation. SPEAR utilizes two specially designed DNA probes linked to an antibody pair that binds to a target protein. Probe A is primarily double-stranded with two short single-strand domains at each end. It also incorporated two chemical modifications in the double-stranded region that act as stoppers, which can stop a polymerase extension reaction at a particular nucleotide position. Probe B is largely single-stranded with several specially designed domains. The short green domain sequences on probe B is complementary to the green domain sequences on probe A. So when the two probes co-localized on the target protein, the increased local concentration will promote the binding between the two green domains. Then a DNA polymerase with strand-displacement activity will extend the probe B until it hits the stopper. After that, the first time extended probe B will dissociate from probe A through a strand displacement process. At this time point, probe B has a new domain sequence that is complementary to the single-strand red domain on probe A. Since they are still in proximity, probe B will bind to probe A again and do the second round of extension and dissociation, adding a purple sequence to probe B. When we throw in a PCR primer complementary to the purple sequences, then only the double extended probe B can be exponentially amplified through PCR reaction. The two probes could also randomly meet each other in solution, conduct the first extension, but it is much lower chance for them to meet the second time and do the second extension without binding to a target protein. So the majority of the extension products will not be amplifiable. This two-step successive extension will significantly lower the background in bulk solution and improve the sensitivity. Here are simulation results showcasing the significant sensitivity improvement enabled by the two-step reaction SPEAR compared to the PA like a single-step reaction. So both simulation uses the same parameters for probe concentration, antibody affinity, reaction time, and the reaction rate constant. PU represents unwanted background reaction in the figure occurring in bulk solution, and the PW star represents the desired reaction from co-localized target binding events. When using a single-step reaction, the signal from 100 femtomolar of a target is barely distinguishable from the background. Meanwhile, with the two-step successive reaction in SPEAR, the signal from as low as 0.01 femtomolar target can be clearly differentiated from the background. This translated to over 4 orders of magnitude improvement in sensitivity when using antibodies with a KD of 1 nanomolar. To experimentally validate the improvement in the signal-to-background ratio, we compared a single-step extension to the two-step extension using body-related probe that bind tightly to a strip of avidin. So what we can see is that 100-fold to 1,000-fold improvement actually can be observed mainly due to the significant background reduction from the two-step reaction. The higher probe concentration used, the more improvement can be achieved, which is practically important for developing assays with antibodies of various affinity. We also simulated the achievable sensitivity of a sphere with antibodies of various KD in the range of 100 picomolar to 10 nanomolar, which is the typical KD range for commercially available antibodies. Sphere can detect down to single copy of target protein from 1 microliter sample when using high affinity antibodies. Even with low affinity antibodies, Sphere will achieve detection limits in the low femtomolar range. Compared to PEA like a single-step reaction, Sphere delivers at least 1,000-fold improvement in sensitivity across a wide range of antibody affinity when using high picomolar probe concentration. To experimentally validate the Sphere's sensitivity, we test its performance using body-related probe bound to a strip of avidin. The result confirmed that the Sphere can detect as few as 6 copies of strip from 1 microliter sample as predicted in the simulation. Moreover, Spheres consistently demonstrate low attomolar sensitivity from 1 microliter sample across various binding systems, including aptamers, antibody, and antigens with various affinity for different targets. This enables reliable detection of less than 100 copy of target protein molecules per sample, making it probably the most sensitive platform for protein biomarker measurement. Here, we showcase an example of a plasma p-tau231 assay developed using the Sphere platform. So p-tau231 is an extremely low abundant biomarker in plasma, and currently no commercial available assay can reliably quantify or detect its level in most plasma samples, even when using large sample volumes. With a Sphere, the p-tau231 assay can readily quantify p-tau231 levels in 100% of a plasma sample, even using only 1 microliter of diluted sample. This demonstrates the Sphere's ability to measure previously undetectable biomarkers with exceptional sensitivity. The ultra-sensitivity of Sphere is robust, less dependent on antibody affinity compared to wash-based platforms. In wash-based immunoassay, antibody affinity is critical for ensuring that the immunocomplex survives through the multiple prolonged wash steps. In contrast, Sphere only required the two antibodies to stay together for a few minutes to complete the two-step extension without any harsh washing steps, meaning even antibody with nanomolar KD may still deliver ultra-sensitivity. To demonstrate this, we developed 3 low-abundant cytokine assays across 3 different platforms using the same pair of antibody. Compared to the digital ELISA, Sphere consistently achieves higher sensitivity with significantly lower sample volume across all 3 assays. More importantly, Sphere shows consistent sensitivity across all 3 biomarkers. Meanwhile, digital ELISA shows significantly lower sensitivity for interferon gamma due to the low affinity of the antibody used. The same, ELISA also shows lower sensitivity for interferon gamma as the digital ELISA due to its heterogeneous nature. The difference in sensitivity have been further confirmed by testing the same serial diluted serum sample with the Sphere and the digital ELISA assays. Sphere successfully detect all 3 cytokines at a higher dilution for the serum sample than digital ELISA, even using much smaller sample volume. This result highlights Spear's ultra-sensitivity and the reduced dependency on antibody affinity, making it a more efficient platform to develop sensitive assays. Beyond ultra-sensitivity, Spear also demonstrated advantage in specificity in 13 cases. Here we present an example of a p-tau217 assay developed using Spear platform. When testing the same plasma sample from CSF confirmed AD and non-AD cohort, Spear assay achieved a significantly higher fold differences and the AUC compared to a commercially available digital ELISA assay. We believe that is due to the Spear assay allows free interaction between antibody and antigen in homogeneous solution, and there is no signal generated from non-specific binding of antibodies to the imperfectly functionalized surface. As a result, Spear assay has higher potential to achieve superior clinical performance in sensitivity and specificity. When further testing 194 plasma samples from CSF confirmed and amyloid PET confirmed AD and non-AD cohorts, we further validated the best-in-class clinical performance of the Spear 2 p-tau217 assay. 100% of the sample were quantified above the functional LQ, used just 1 microliter of diluted sample. More than 5.4-fold difference has been achieved between the control and AD cohort with an average AUC above 98%. This assay has been recently granted FDA breakthrough device designation for its potential in identifying or ruling out amyloid pathology in AD. Unlike other advanced technologies, Spear actually offers an exceptionally simple workflow, requiring only 3 rounds of reagent adding and mixing directly into the same tube or well before putting it on a qPCR instrument for reading. The simple workflow without error-prone wash steps ensure highly precise measurement from Spear assays. When automated workflow with a benchtop liquid handler and a small footprint shaker, less than 5% CV can be readily achieved with 1 microliter volume of sample, either in a 96 well format or a 384 well format. Even at the lower femtomolar concentration, no sample measurement exceeded 20% CV in the 2 assay example here. The total assay time is about 3.5 hours, including qPCR reading, and with only about 20 minutes of hands-on time. This is another example of the high precision and the repeatability of Spear assays. In another study measuring 78 plasma samples from an amyloid PET confirmed cohort using the Spear p-tau217 assay, result shows that high repeatability across 2 independent runs, maintaining the same clinical sensitivity and specificity using the same cutoff. All plasma samples were measured above the functional LQ, again, with intraplate and interplate CV both below 5% and using just 1 microliter of diluted sample. Beyond the sensitivity and the precision, Spear also delivers excellent measurement accuracy. In a comparison study of 36 plasma samples, the Spear NFL assay was benchmarked against 2 well-established commercial assays, which is the SiMoA NFL assay and the MSD-S-Plex NFL assay. Spear demonstrated perfect concordance with both assays, consistently aligning across high and low concentration samples. With ultra-sensitivity and high precision, Spear is actually an ideal platform for developing assays tailored for microsampling and longitudinal studies. Here is an example of how Spear enables high-frequent longitudinal monitoring using finger stick dried blood spot samples to track mRNA vaccine response. A COVID spike protein assay and a spike pan-Ig assay were developed using Spear platforms. Through longitudinal sampling, we could clearly track a spike protein expression following the first dose of both Moderna and Pfizer vaccines, then followed by an increase in anti-spike pan-Ig levels. The higher spike protein expression observed with Moderna is consistent with its higher dosage. Additionally, a second spike in pan-Ig levels were also observed following the second dose of both vaccines. The combination of Spear's ultrasensitivity and microsampling presents a powerful solution for large-scale longitudinal studies, particularly in neurodegenerative disease research. That brings us to the end of today's presentation. In summary, Spear technology offers unprecedented sensitivity for protein biomarker measurement while maintaining a simple wash-free workflow. We believe Spear has the potential to be a game-changing tool for developing blood-based biomarker assays addressing long-standing challenges in the neurology space. I hope this session has provided valuable insights into Spear technology and its advantage as an ultrasensitive homogeneous immunoassay platform. Thank you all for your time and attention. I will now hand it back to Oliver for some closing remarks.
Thanks again, Feng, for the great presentation on the Spear technology. Before we go, I'd like to thank the audience for joining us today. Questions submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand for 1 year until March 5th, 2026. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. I want to thank everyone for attending today's webinar. Have a great rest of your day.